When we write chemical equations, we know some rules for writing formulas, whether they are molecular formulas or ionic formulas. But for some elements, we need to write their formula in a special way. And this is due to the nature of their individual reactivity, and when they exist by themselves in nature, they don't exist as single atoms. There are 7 elements that exist in 2-atom molecules when they are bonded to each other. And so whenever we encounter an element in a chemical equation that is by itself and it is a diatomic in nature, we need to remember to automatically write a 2 as a subscript following the formula. Usually our subscripts are based on differences in charges, and so we might use the crisscross method, or it is based on the prefixes that are used in the name for the compound. This is one of the rare instances where we automatically put a subscript just based on what the element is and the fact that it is by itself. So to determine, or to remember rather, these 7 elements, and the 7 diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are a couple of different ways that you can use to remember it. There are a number of mnemonics out there that people have used to remember these 7. But 2 methods that I think are particularly useful. One is called the rule of 7s. And as the name indicates, 7 is a very important number to this memory scheme. First of all, there are those 7 diatomic elements that I mentioned. To find them, if you have a periodic table, start with element number 7, which is nitrogen, one of the diatomics. And hydrogen doesn't fit into this pattern, but it's the first element on the periodic table, so it shouldn't be too difficult to remember. Along with hydrogen, you start with element number 7, nitrogen, and then you literally trace a right angle 7 on the periodic table to find the remaining diatomics. So that right angle 7 will trace you over nitrogen, oxygen, fluorine, chlorine, bromine, iodine. It's kind of neat how it works out that way. That set of rules may not work for everybody, so if you are better with mnemonics, words that you use each part to remind you of a specific portion of it, you can remember our good friend Dr. Brinkelhoff. And the way you spell Dr. Brinkelhoff's name corresponds to bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. May not be in the same order as we find on the periodic table, but again, it gets you all of your diatomic elements. So whenever you encounter an equation that you are translating from narrative form or word form into symbolic form, if you see that you have one of those 7 elements and it is by itself, it is not combined with any other element, you have to remember to automatically put the 2 in as a subscript. When we are presented with a narrative description of a chemical reaction or a word equation, we need to use the context clues that are provided within that narrative to determine, first of all, what are our materials that we are starting with, our reactants, and what material or materials are we ending up with, our products. Once we've determined what our reactants and products are, then we need to make sure that we write their formulas correctly. And oftentimes this is going to involve us looking up their charges if it's something that's ionic, checking if those charges don't cancel out immediately, using either the algebraic method or the crisscross method to get the proper ratio of elements. If it's molecular in nature, we use the prefixes to help us get the proper subscripts. And we need to remember that anytime we have an element that's all by itself, we need to double check, is it one of those 7 diatomics? And if it is, we automatically put a 2 as a subscript. If it's not a diatomic, then it can stand alone on its own. So if we take a look at an example, we have the statement, when solid calcium carbonate is heated, it forms calcium oxide and carbon dioxide gas. The first thing we need to do is to evaluate this statement and determine what are our reactants and what are our products. Based on the context clues that we have here, it appears as if the calcium oxide and the carbon dioxide are coming secondary. And that's because the statement says that it forms calcium oxide and carbon dioxide gas. The heating of the solid calcium carbonate is what's happening initially, and therefore the calcium carbonate is our reactant. So we start by writing the formula for that reactant. Calcium being Ca, it's an alkaline earth metal, so it's going to have a +2 charge. Carbonate is a polyatomic ion with a -2 charge. Those charges cancel, so no crisscrossing is necessary. We're also told that it is in the solid state, so we'll put a subscript S in parentheses. Now, because this is the only reactant that we have, this is a decomposition reaction. Decomposition reactions are indicated by the presence of only one reactant. So we'll put our reaction arrow, our yields arrow, and now we'll write the formulas for our two products. Now, carbon dioxide, we're told, is a gas. Calcium oxide, there's no indication of what the state is, but if we think about it, we're starting with a solid, and we are heating something to the point where it decomposes, it's degassing, giving off carbon dioxide. So what's going to be left are calcium and oxygen, and there's no indicator that there's no water present, so we don't have to worry about solubility. Most likely, this calcium oxide is going to be in the solid state. But in terms of writing the formula, again, calcium is a +2 charge. Oxygen coming from group 16 is a -2 charge. Again, charges cancel, so the formula is simply CaO, and we would put S for the solid state. A bit of an assumption there, but a safe one. Plus, our secondary product was carbon dioxide gas. So here is a molecular name. We can tell that because of the prefix. So to interpret that properly, we use CO2. Only one carbon, absence of a prefix, and the fact that it says it's a gas, we put a subscript G following that. Taking a look at another example, we have elemental copper and aluminum chloride that are formed when aluminum is added to a copper 2 chloride solution. So if we evaluate and try to determine which of these are going to be our products, we see that, in fact, here the products are listed first and the reactants are listed second, which is why it's important to critically read the statement and not just assume that it's going to be put in order. Reactants first and then products. Okay, it's saying that the elemental copper and the aluminum chloride are formed when you do something else. Here, particular aluminum plus copper 2 chloride solution. So writing our formulas, aluminum, element by itself, double check, is it diatomic? It's not one of those 7, so we can write Al by itself. And using what we know about aluminum from our own personal experience, as well as looking on the periodic table, we know that it's in a solid state under normal room conditions. So we put an S by it. Plus, we have copper 2 chloride solution. Whenever you see those Roman numerals, you know automatically what the charge will be. Chloride, being a halogen, is going to be a -1 charge. The charges do not cancel here, so we will need to either use the crisscross method or algebraic method to get the proper ratio, and we find that that is 1 copper to 2 chlorines with the formula CuCl2. We're told this is a solution, and whenever we see solution, we assume that it is an aqueous solution, and therefore our state would be represented by AQ. That's it for our reactants, so we put our yields arrow, and now we proceed to the products. Our first product is elemental copper, so it's Cu. Again, check if it's diatomic. It is not, so Cu is fine by itself. And again, using our own personal knowledge of copper, as well as looking at the periodic table, we see that copper is a solid under normal conditions, so we put the subscript S. Plus, our second product, aluminum chloride. Aluminum has a +3 charge. Chloride is a monatomic anion with a -1 charge, and again, the charges do not cancel, so crisscrossing gives us AlCl3. Alright, and aluminum chloride will come upon a tool in a little while called the solubility rules, which will help us to determine whether or not a particular substance is in fact water soluble or not. For right now, we'll work under the premise that aluminum chloride is aqueous. Now, one last thing that we can identify by looking at the formulas for this equation is what would we expect to see visually coming from this reaction. We know we're starting with solid aluminum, and we've got this copper solution. So we're putting a solid into a liquid. And what we're going to get is still a liquid, a solution, plus another solid, but the solid is different. And if we use what we know about the appearance of aluminum versus copper, we can predict that we ought to be seeing the formation of a reddish type solid because copper has a reddish color. Not only that, elemental copper is not water soluble, so it is going to be generating a solid in solution, something we call a precipitate. And most precipitates are going to fall to the bottom of the container, the reaction vessel. And so the way that we denote this, besides putting the S for solid, is oftentimes you'll see a downward arrow written immediately after the formula. And that's just another visual cue to let you know that you should be observing something directly falling to the bottom of your reaction vessel. Sometimes when a gas is generated, besides the G as the subscript, you may also see an upward arrow because your gases are going to be more buoyant. Now, besides all of those different notations and what they can tell us, the important thing to note here is we've got the same number of aluminums on both sides and the same number of coppers, but somehow we seem to have gained a chlorine atom. And this is a violation of the law of conservation of matter. So we call this type of equation, where we have translated it from word form into symbolic form, we call this a skeleton equation. And that is because it's a bare bones equation. All we know are the reactants and the products and their proper formulas. What we don't know is the proper ratio. So the skeleton equation needs to be balanced.